Hello everyone, welcome to my talk. Today I want to talk about the so-called transport information Hessian distances. Uh, at the beginning, let us quickly review the history of statistical divergences. So people at the beginning, we are interested in so-called the Euclidean distances, and there's some quadratic distance and some Riemann distances, so on and so forth. In particular, in statistics and in the AI, in machine learning, and in many applications, also in physics, we are very interested in the so-called entropy, which is P log P. And also we use this entropy and its second order properties like a Hessian metric. We introduce a lot of interesting divergence functions. As we know, divergence is we have some interesting asymmetric properties, and its particular one involve the log function, which is very interesting. So one of the most, I would say, arguably the most important ones here is so-called the Kullberg-Leberger divergences. People also call it the relative entropy. And very close to this so-called the Hellinger distance is right in here. It's square root of P1 square root of Q squared, up to some constant here. And also, the information geometry is kind of way, study this Hessian metric and study different generalizations and construct different, interesting divergences, in particular the alpha divergences. So in this talk, I try to, apply the other type of distance function, so-called, people know it very well in the recent years, it's so-called optimal transport, or people call it orthomorphic distances. And we try to build this picture. In particular, I'm using entropy, I'm using the optimal transport distances. I try to construct some, a new type of Hessian distance functions, a new type of divergence functions later on to fit this picture. Okay, so that's the goal. So before I talk about very general, like in the optimal transport space, we operate these things. Now let's come back to this classical example. What does this distance and divergence should look like? Okay, so given some points, let's call the x and y. Let's say in the one-dimensional space, can also be some abstract space. The divergence function between them is defined below. Okay. So one way is just like just take the difference of them into the squared. So this is called the squared Euclidean distance. Or you can consider so-called the Kullberg-Leberger divergence, which means you take x log x over y. Or you can consider some so-called the squared Hellinger distance, which means you take a square root of x and a square root of y squared and times 4. Okay. So later on, we will build each of them into the optimal transport. Sometimes people call the Western space. And in particular, the squared Euclidean distance will be replaced by the optimal transport distance. And we will build each individual term following the optimal transport structure. Okay. So basically, I view optimal transport space as a particular space. In this space, I try to build some new distance or divergence function nodes. Okay. Now, what is KL divergence? So let's quickly review it. Okay. So understand the KL divergence will allow us to understand that it's Hessian distance, so-called the Hellinger distance, and then it will help us to build our own analog of them. So one important of divergence function is so-called the KL divergence. Now it is defined by integration P log P over Q. There are two distinguished features of them. One is you study P over Q. Okay, so it's not a very symmetry behavior because Q over P and P over Q are different. The other thing is like you take the log of them, which later on in applications is very important, has many interesting applications. Now, basically, you take log P over Q and you average over P. Then that's the KL divergence. As I said, since you get the log of them, you have a non-symmetry, and it's also separable, and it's convex in the L2 space relative with respect to P and Q. So it's very nice kind of function to measure the difference between P and Q. Now, as known in the literature, there's a Hessian metric behind, for the KL divergence, and later on you can further use this Hessian metric by changing the Levi-Civita connection to construct other divergences. Okay, that's the study of information geometry. Now, let's look at what is Hessian metric here. So we just do a very simple computation. We do nothing but take the some perturbation on the P. Let's call the Q plus Q dot. Q dot is just a tangent direction for the Q, and you just do Taylor expansion, and you will figure out in fact this the corresponding term for this expansion is give you this GQ of Q dot Q dot, and this GQ Q dot Q dot essentially the H should be Q dot. In fact, it gives you the quadratic form for the Hessian operator for the KL divergence. For this, the Hessian operator for the negative entropy and negative Boltzmann entropy, and this GQ is called the Hessian metric, and in the L2 space, and this so-called Fisher-Rao information metric. Now, basically, giving a metric, we can try to construct the distance function. Essentially, it's just like by a simple change of variable. You just inf all the paths from 0 to 1. Maybe from 0 1 times omega to r, and you just consider this Hessian metric, and you let gamma 0 equals p, gamma 1 equals q, and you try to minimize all the passes. Okay. Now by some simple computation, in this case, you get this partial t gamma over gamma. This is dt dx here, and you do a change of variable, which is 2 of partial t square root of gamma. This one will give you this term, okay, when you take a square of them. So then, when you write it into this form, along the square root of that function, this is flat, and then you can try to plug in the solution. Then you get this kind of formula, which is square root of p minus square root of q, square root of dx. Okay, so this is so-called the Hillinger distance. So, and this is the so-called the Hessian distance function. Now, from this several line, if I know some Hessian metric, I should expect, I should modify my Euclidean metric, which is like, in this case, L2 metric, p minus q squared by square root p minus square root of q squared. Okay, so Hessian metric tell you there's a simple change of variable which allow you to change this original distance function to a new distance function. Okay, and for this Fisher metric, this kind of change of variable is very easy to be observed. Okay, so everything here is very classical in the Euclidean space or in the L2 space, and you will get different functionals. Now, in this talk, we are mainly interested in the other space, which is not the L2 space, which is not the Euclidean space. It's so-called, people call it Orphan transport space. Okay, now what does this mean? So there's a very interesting story behind it. Basically, you have two densities. It's called one with the shape X, the other is with the shape Y. You want to find the best way to move or transport one mountain from X with shape X to another shape with density P. Okay, so basically you want to find a best mapping function to map one density to the other density, and you want to minimize the kind of like L2 type of the cost in terms of mapping between them. Okay, again, this becomes a very interesting problem, and Munch, Kalanovich, Weissenstein, or Samover all correspond to this kind of meaning. So it's find the best transportation to move one density to the other one. Okay. Nowadays, this distance is also shown very powerful in statistics problems. That's why all different groups try to study it. Now, in this talk, we try to do something different. Okay, we try to say, okay, can we follow the classical study of this using entropy to construct a distance, this kind of story, to work on the optimal transport space. Okay, so suppose I already have an optimal transport distance. Can we do some modification using the entropies information and to gain some new distance? Okay. Now, to do this, there's a lot of interesting motivations. One of them is like, distance function somehow, people rarely use L2 distance to measure the two density, because L2 distance somehow is not that simple in the sense that it's asymmetric, very important probability, asymmetric property is not there, right? The other thing is like, so there's very important property of entropy we have to inherit, try to measure the difference of the densities. Okay, that's the goal here. We try to borrow ideas from entropy to derive a new distance, which is this new distance directly inherits these Hessian operators of the entropies. Okay, so that two questions: what are the Hessian distances in Western space? Okay, now here I'm talking about Western space. I'm talking a very simple one. Let's say Western 2 space. And what is the Hillinger distance in the Western space? Okay, there are related studies by Amari and Guo and Guo et al., Leonard et al., and Nihai et al. So they are all working on the thing around. But in this talk, we try to provide you analytical formulas which demonstrate this very, very close study behind information geometry and optimal transport. And in particular, they are analytical. Our geometric features, see my previous works, I compute them. So from this computation, I observe this, essentially, optimal transport belong, at least Western 2 space belong to a special classes of information geometry. Anyway, so let's do some analytical computations. So in one-dimensional space, the optimal transport distance has a closed form solution. It's nothing but tx minus x squared times qx, as I said before. And here t is so-called is a non-neutral mapping function such that pt times t prime equals q. Okay. So by some calculations, you will find it's very easy to be computed. Essentially it's fp inverse y minus fp q inverse y squared dy. Here fp and fq are cumulative distribution of pq respectively. So in one word, somehow in one dimensional space, things is so simple. The mapping is you can solve the mapping, and they are flat in the sense of fp inverse. Okay, so in the inverse of this transport, in the inverse of the cumulative functions. Now, a known fact in the literature is follows. Okay, so by many previous also you can see the Amricia Gigli and Savary and Valani's book, and many people already demonstrated this. So essentially, you can derive the second order property, property of this F entropy by computing, along the geodetic, you compute the second derivative of the entropy functional, and you will find the following byproduct. And this is we call it the Hessian metric. Okay. A long story short, this is the continuity equation generated by these mapping functions, and you have to consider the second derivative of your entropy times p squared and times the Hessian of this phi squared. Okay. So here I will only work on 1D. It looks like this. In general, you have to have some Hessian and some Laplacian squared. Okay. So it's not that simple in high dimension. Okay. Now the goal here is according to this kind of PDE type metric, believe it or not, we can still manage to find the closed form solution for this Hessian distance. That's the second that's the main result of this paper. So essentially there's a additional change of variable there in the optimal transfer space. If you give me the entropy, the F entropy, I just do this kind of integration. I introduce a function I called h of y, which is equals 1 to y square root of f double prime 1 over z times 1 over z 3 over 2 dz. Okay, using this function h, I can allow me to write down the Hessian distance explicitly. Okay, Hessian distance in the optimal transport space explicitly. So it's given below. It's very simple. It's h greater than y of fp inverse minus h greater than y of fq inverse, and you take the square root dy. Okay, so basically, this choice of h depends on which entropy you create. It depends on the Hessian information here, and somehow you can view the follows. So h itself is you build some new distance based on the gradient operator of your mappings. Okay, so that's the mapping formulation right here. Essentially, you can do a change of variable again, similarly like the optimal transfer distance format. Essentially, it's gradient x of t over q minus h gradient x over t over q minus h 1 over q squared times q dx. Okay. So essentially, again, t is the optimal mapping function. So basically, this kind of Hessian distance tell you the following effect. We take additional derivative of the mapping, and in the gradient operator, gradient of the mapping, we measure a new distance, and this is weighted by some function of h. H depends on the Hessian of the F entropy. Okay, so it's very close formulas. This is very, very close to this Hillinger distance if h. In most of the case, h can be some power function or even the log function. So it tells you how the, formula-wise, you just treat the gradient of x of t by this p over q, okay? Kind of a p over q. So this gives you this measures how the ratio, gradient of x of t measure the ratio between p and q. That's something interesting behind this formulation. Now, in the end of this talk, I try to give you one example, which I believe is one of the very, very important example, and I will try to connect to the KL divergence very soon. So I choose P, Fp as P log P, which means I can see the entropy. And in this case, I can integrate this formula. I can find the solution, which is negative log Z, and I plug in, I find this formula. So essentially, it is log of gradient x t squared times q dx. Okay, or you can also write gradient f gradient y fp inverse and gradient y fq inverse y squared dy. So this formula mimic the rule of Hillinger distance. Okay, so basically at the beginning I have fp inverse and fq inverse squared. Somehow I do some gradient operator here and do some log operator here. I can construct a new function for it and minus the corresponding q function. And that's one is my which way I call it the transport Hillinger distance. Okay, I mean there are a lot of interesting analytical formulas. Once you have this, we can compare different family of probability densities. But here we see the closeness between optimal transport and information geometry. When you look at the entropies and apply these concepts, you will see a lot of interactions. In the last, this is without giving too much detail. Once you see this kind of relationship, it's not hard to see. We can also construct the so-called the transport KL divergence behind this Hessian distance. Okay, follow the exactly same idea of information geometry. You can do the following thing. This is, gradient y fp inverse, gradient y fq inverse minus log gradient y fp inverse, gradient y fq inverse minus 1. And you do the integration. And this format, again, I want to say, this format tells you this is a Itochi Sato kind of divergence. It's which I call the transport type divergence. Okay, and you can also compare it with KL divergence using FP and FQ formulation. So basically, there are some polynomial changes according to this, what I said before. And you also have change from gradient of FP inverse to gradient of FP. So that's the difference behind this divergence function of in L2 space and divergence function of in the Western space. Okay. I think my time is over, and thanks for your listening.